We're going to wrap up now by looking at a couple more problems, the sort of problems you might see on an exam. These are predict the product and or reagents that are required to show the desired product. But basically I refer to them all as predict the product type problems, even if it's the reagents that we're predicting. So for example, here we're starting with this trans-2-butene, and the question is, how would you make the oxirane that is shown? And what you want to notice is that the oxirane has 4 carbons, just like we had here. So the skeletal system or the scaffolding of the molecule has not changed. We've got 4 carbon scaffolding here and a 4 carbon scaffolding here. We even have the same stereochemistry. This is trans, and in this oxirane structure we've got trans methyl groups. So clearly we're looking for a reaction that's concerted, that will maintain the stereochemistry that's present in the trans-2-butene. And hopefully you recognize that the way to get from there to there is using a per acid like MCPBA. So that would be the answer to that problem. You simply show the reagents that are required to get you from starting point to target. Over here, we're going to actually predict the products of a different reaction, or product I should say, of a different reaction. This is diazomethane, and under these conditions where we shine light on diazomethane, we make a carbene which can cyclopropionate alkenes. That's also a concerted reaction, and so when we cyclopropionate the alkene, we're literally adding methylene across the pi bond, this methylene right there of the diazomethane. Because it's a concerted reaction, we will lock the stereochemistry in place. In both of these cases, we've made optically active compounds, or at least it looks like we have. But we know that's not possible since we started with optically inactive alkene, so we must be making racemic mixtures in both cases. All right, very good. And then finally down here, we're going to predict the product of this ozonolysis reaction. This is ozone in the first step, followed by dimethyl sulfide. And we need to know that dimethyl sulfide is a reductive workup reagent. And so in this particular case, when we chop the alkene in half, these hydrogens are not going to be oxidized further to OH groups, making carboxylic acids. Where under reductive workup conditions, those hydrogens will just simply stay in place. We chop this alkene in half, and we get 2 equivalents of this aldehyde. And again, because we're under reductive workup conditions, the aldehyde is the final product. So that was nice and easy. 3 different predict the product type problems of an alkene using reactions we've just learned. Let's now finally finish up by looking at a couple of synthesis problems. There are really 3 types of problems we need to be familiar with in organic chemistry at this point moving forward, and they are predict the product type problems, which we just did, and you've done a lot of those in the last few weeks. They are mechanism problems, where you draw out the mechanism for a reaction. When you draw out the mechanism, you need to show all the little nitty-gritty details from start to finish. And then finally, the third type of problem is the type we've got here, a synthesis problem. We've got 2 synthesis problems here. We are trying to convert this starting material into this target in our first synthesis problem, and then into this target in our second synthesis problem. And you see that these 2 targets are very closely related to each other. They're both vicinal diols, but in one case they are syn vicinal diols, and in the other case they are anti-vicinal diols. All right, so here we go. How are we going to do it? Well, if you think about the reactions that lead to vicinal diols, they're not reactions of alkynes. They are in fact reactions of alkenes. So what we might like to do is to convert our alkyne into an alkene in order to produce these 2 different structures. We do know how to do that. In fact, if we take our alkyne and we treat it with hydrogen in the presence of Lindlar's catalyst, then we can produce, with syn addition, the corresponding Z alkene. Syn hydrogenation gives us the Z alkene. Look at the vicinal diol we're trying to form and the alkene we've currently got in place. We know two different reactions that can get us there. The first is osmium tetroxide followed by sodium sulfite, and that will give rise to the syn vicinal diol. We can also get there using a different reaction, potassium permanganate, in the presence of aqueous basic solution. So two different ways to get from that alkene to the syn vicinal diol. So these would represent nice syntheses starting from the alkyne, leading through the alkene, and ultimately to the vicinal diol with syn stereochemistry. What about the anti-stereochemistry? Turns out we do know how to do that as well. Let me get a fresh sheet of paper here. If we take the same alkyne starting material, and once again using the same reaction, H2 in the presence of Lindlar's catalyst, go ahead and produce the corresponding cis 3-hexene. We can take this and convert it to an oxirane. And when we do that, we get an oxirane that looks just like this. Now what we know is that if we want to make the anti-vicinal diol, we can do it in two different ways. We can either use H2O, H3O plus hydrolysis conditions, or OH minus H2O. That is either aqueous acidic or basic conditions. Either one will do the job. To produce the corresponding anti-vicinal diol. So those are a couple of synthesis problems. In class on Friday we'll look at more homework problems and more that could include more synthesis problem, more predict the product type problems, more mechanism problems, whatever you'd like to do before the exam on Friday. So what you need to do to prepare yourself is to make sure you work on all the homework so that you come to Friday's class with a lot of good questions about those homework problems. Review your book, review your notes, review this video, and you'll be in great shape. I'll see you Friday.